Before we start diving into the material in this section / chapter, I'm going to do a quick review with inverses with you in case it's been a bit. So if we talk about inverses in math, what we're talking about things that undo each other. So addition and subtraction are inverses. They undo each other. Okay? If we talk, that's a subtract. If I talked about multiplication and division, those are inverses. They undo each other. Logarithms and exponentials are inverses. They undo each other. Squaring and square rooting are inverses. They undo each other. So when we talk about inverses in the context of trig, we're going to have to introduce some new notation. But what we want to do, first of all, is recognize that if the inverse of a function is still a function, if the inverse of a function is still a function. So what we're going to do is stay in algebra world for a second, and we're going to go back to our friend the parabola. So here's our friend, the parabola. He is y equals x squared. And when I graph him, he looks not drawn to scale, but he looks like this, okay? In a perfect world, that would be a perfect parabola, but I didn't draw it that way. So this is my parabola. Now, is he a function? Yes, he is, because I can draw an infinite number of vertical lines, and each vertical line will hit the picture of the parabola a maximum of one time. Okay, so once, all that kind of good stuff. Now, first thing that I keep saying first thing, and now we're on to like thing number 8. Okay, so what we want to do is remember how to find out if the inverse of this parabola is also a function. So I'm going to take you through how to find it first, and then we'll find a shortcut, okay? So what you want to do is you want to flip-flop your x's and your y's. So instead of y equals, I'm going to have x equals, and instead of x squared, I'm going to have y squared. And then I just want to solve for y. So y is almost by himself, but I've got to kill that square. So anytime during the process of solving a problem that you need to take a square root, don't forget your plus minus. So what I have right now is y equals a positive root of x, which looks like this, okay, and a negative root of x, which looks like this. And you'll notice that these things are symmetric across the line y equals x. So symmetric across y equals x, which I put at instead of across, but whatever. All right, so here's what's important to recognize. When I'm looking at the inverse of this thing, it's symmetric across this line, which means if I lay my hand down here, my thumb is in quadrant 2, corresponding to this arm, and my pinky is in quadrant 1, corresponding to that blue arm. I am not rotating. I'm not doing this to where this arm becomes that red thing and this arm becomes that red thing. I'm reflecting, which means my thumb in quadrant 2 associated with the blue part is corresponds with my thumb in quadrant 4 corresponding to this red arm. Okay, now look at my pinky. My pinky is in quadrant 1. I reflect, so I flip. And then what I have is this blue arm corresponds with that red arm. So it's not a rotation. It's not doing this. It's saying my fingers are going up right now. I'm going to reflect them so that they go across. So my question now becomes, is that red thing a function? And you should say immediately, no, he is not a function, because an infinite number of red lines, red vertical lines, cause that red sideways parabola to fail the vertical line test. So let's go back and let's re-rotate this red graph. So remember, I've nailed down this vertical line, so he is attached to my red function. So what happens when I rotate this thing back up so that the red thing is lying on top of the blue thing is this vertical red line now becomes a horizontal blue line. Okay, so what I can do is I can use a vertical line test to determine if my original function is a function, Or I can use a horizontal line test on my original function to determine if his inverse is a function. So I don't have to map the inverse. I don't have to find the actual equation for the inverse. I can just look at my original blue parabola and say, okay, you're a function. You passed the vertical line test. But your inverse is not a function because he fails the horizontal line test, which is this vertical red line on the rotated red part. So that is your basic quick review. Also remember, since you're flip-flopping your x's and y's, if my original function and my inverse, which is noted with a little -1, it's not an exponent, it's notation. So that is not an f to the -1. That says the inverse of f of x. Okay? If I'm flip-flopping my x's and y's, then the domain for my original function, which is your x's, becomes the range for your inverses. Okay? Your range for your original function becomes the domain for your inverse. So all your x's become your y's. All your y's become your x's. Okay, so now let's put that in the context of trig. If I have the sine of an angle equals a ratio, okay, then the inverse of that will be the inverse of sine of a ratio will give me the angle. So how do we write inverse? So the inverse of sine, we're going to write one of 3 different ways. So I can write the arc sine, and similarly I would write arc cos for arc cosine and arc tan for arc tangent. So arc sine, arc cosine, arc tangent, arc cotangent, arc cosecant, and arc secant. I shorten that and I just put an A out front. So the arc sine, okay? And there are publishers that when you enter this, it will recognize it as the inverse. But technically, you're supposed to put ARC and then the trigonometric abbreviation. Another way to do this is to say the inverse of sine, and then you would have of y equals x. Why? Because you flip-flop your x's and y's. So this is 3 ways to write this, and I'm going to end up writing this a whole lot more like a sine, just because it's a little bit cleaner and faster, and math people are lazy. So we need to restrict our domains. So if you will look at the notes, I'm trying to find mine. Look at the notes that I uploaded into Canvas for you, and you'll see this lovely little thing in the corresponding week that we're in, and it says inverse trigonometric functions. So first of all, notice that an inverse is not the same as a reciprocal. A reciprocal is when I flip or invert my fraction, okay? So an inverse undoes something. And then I can read this as the inverse of sine is to be read as inverse sine or arc sine. And then what we're going to, from there, you're going to look and see that the sine of an angle equals the ratio, but the inverse of that is the arc sine of the ratio equals the angle. So the input and the output flip-flop. So there are 6 trig functions that we study. There are more than that, but we study 6. There are sine, cosine, tangent, cosecant, secant, and cotangent. I don't know what I just said. There's those 6 right there. All right, so every single one of those passes the vertical line test. So every single one of those are functions. So what I need to do is look at a horizontal line test. So I'm going to look at page 2, and what I've done is I've graphed the sine curve. So recognize it goes on and on and on forever and ever and ever, both directions, left and right. So this little part between 0 and pi over 2 references all of the ratios in quadrant 1. Between pi over 2 and pi references all the ratios in quadrant 2. And between pi and 3 pi over 2 references all the ratios in quadrant 3. And between pi over 2 and 2 pi references all the ratios in quadrant 4. And that's when we're referring to the unit circle. So remember, come back over here. Let me find my circle. He is missing. Okay, so quadrant 1 right here is between 0 and pi over 2, and it references all those angles. Okay, then pi over 2 to 3 or to pi So pi over 2 to pi references all of the ratios in quadrant 2. Okay, so that's how we're going to map that thing out. Now, he passes the vertical line test, but he fails the horizontal line test. So what we want to do is called restricting our domain. So I want a representation of every single y value that can pop up. So I notice if I chop this off from 0 to pi, I've got a duplicate of all of my positive y values. So that's not an option. I could say, well, let's chop this thing off. And notice I've got all my positive y values and all my negative y values, but that's really inconvenient. But look if I go to the left. If I go to the left, my range for sine is from -1 to +1. So I have every single y value represented. But I need to move directly from quadrant 4 into quadrant 1 in order to do that. So here's what we're going to look at the bottom. I've graphed you a sine function. Okay, so he goes on and on and on for all eternity. And then I restricted my domain to go directly from quadrant 4 into quadrant 1. So when you're looking at your unit circle, I cannot go around and invade quadrants 2 and 3. If I need quadrant 4, I'm going to have to drop down into it. So I'm going to move from quadrant 4, which is negative pi over 2. And I'm going to keep moving, and I'm going to sweep up through positive pi over 2. So what I did was I went from negative pi over 2, which is right here, to positive pi over 2. So this is just the graph of sine with my domain restricted from negative pi over 2 to positive pi over 2. Your range is still from -1 to +1. And then you'll notice I made a really, really pretty purple picture. So I showed you this is quadrant 1, 2, 3, and 4 if we unroll the unit circle. But I needed to go back so I could move directly from quadrant 4 using negative angle measures into quadrant 1 using positive angle measures. So this purple thing is the graph of the arc sine of X. Not the red, not the green. I know my colors. This is green. Not the green thing. The green thing is this. I'm just using it so you can see that if I fold it across the line y equals x, its arms will lay on top of each other. Okay, so it is symmetric. And now what I've done is I've represented every single potential ratio that exists for sine. Okay, so we can find values for arc sine by dropping down on the unit circle into quadrant 4. To negative pi over 2. So again, you cannot travel around. I have to drop down into quadrant 4, so I move directly from quadrant 4 into quadrant 2. Now, I also gave you sine. Sorry, that was sine. I also gave you cosine. Well, now if I start at 0 and go to pi, I max out at +1, and I min out at -1, which means I already have every single y value represented. So I can chop off these arms going to the left and going to the right. I don't need them. So I'm going to restrict my domain for cosine to go from 0 to pi. So again, I made you a cosine graph. Then I chopped it off. Okay, so this graph right here is represented right here. And then I graphed the arc cosine or the inverse cosine function. So notice again, if I fold it on the diagonal, his pretty little arms will lay on top of each other. So if you're seeing this the first time, I made a typo because I did this really late last night. So it says the domain of cotangent will need to be restricted to the same domain as cosine. Okay, so I actually just rewrote cotangent. So I'm fixing that, but just in case you haven't got the fixed version, make sure you change that to cosine. Now, I've explained all of these for sine and for cosine, but I didn't explain all of them for cosecant, arc cosecant, and that kind of stuff. So I just went ahead and showed you the restricted domains. And then I showed you the graph in purple of the inverse function. So I restricted the domain, and I showed you the graph in purple of the restricted arc secant function. So this is your inverse function. I put a star there because this is like purple and this is hot pink, and it was bothering me. So I need to fix that too. All right, so here's your restricted function from negative pi over 2 to pi over 2. Here's arctangent in purple. Okay, here's your restricted cotangent going from 0 to pi. And then there's your purple inverse which would be arc cotangent. So that's your introduction to inverses, and that's going to help you in section 8.1 and 8.2, or all of the inverse sections that we cover. So I'm going to start giving you examples in the next video.